kids. Today I will be, delivering a unique topic yet again. It's a miscellaneous topic for physics. It's again not discussed in IGCSE. It's actually discussed in grade 8, but I don't think most of the students actually take it very seriously. And this, you know, topic actually has very serious implications for physics and advanced physics once you go into O levels or A level studies. So I'm just going to go with it. It's called physical quantities and units. In grade 8 you don't get to study this in much detail, so I'm going to give complete detail of this topic. So what are physical quantities, right? Physical and quantities, right? So when you write this word, from this we very well understand that physical means something that is physically perceivable, that can be touched and felt. That is what we call as physical. And quantities means something that needs a measurement, right? So if you do know, in IGCSE we have this first unit known as measurements, right? But in that unit we don't actually acquaint ourselves with this topic of physical quantities or units, right? And that's why most of the students in O levels, once they come from grade 8, as I said, they don't take this unit very seriously in grade 8. So once they get into O levels, they are not able to differentiate between quantities and units, and most of the time they actually confuse the symbols of quantities and units. So I'm just going to clarify this topic in detail. So what are physical quantities? Physical, again, which is physically perceivable. So I'm just going to say what you can touch or feel, right? I'm just going to feel, touch. So we're just gonna put it right there. So what are physical quantities? These are quantities. So let me just define these as this. Let me just reduce a little bit. Yeah. Okay. Now uh, these are the please don't mind my joining writing. I'm narrating as well. So uh, these are quantities which uh, can be measured, right? Can be measured uh, and uh, provide basis, right? Uh, for calculations in physics, right? So I'm just going to it's a you can say a generalized idea of what physical quantity is to be perceived as, right? General calculation of parameters, right? Parameters in physics, right? So what is a parameter? Again, we use the word parameter when we're talking about the word quantities, right? So physical quantities, I will divide that into two types. We have two types of quantities. We have uh, base quantities, right? And then we have uh, you can say derived quantities. Right. Okay. Now, as the name suggests, derived quantities are those quantities which are actually extracted from base quantities. So these quantities actually, uh, you know, are taken or derived from the base quantities. Now there are seven uh, base quantities, right? And I will list all those seven. But derived, there are numerous derived quantities. We're just going to touch a few for your course, because this actually is a very big topic when once you take into account. So I'm just going to write these down. Number one, and the most important, is length, right? Number two, we have, okay, let me just tabulate this so that you have much better clarity of what we're doing. I'm going to tabulate this in terms of the name of the quantity, right? The symbol of quantity, and then the unit, uh, right? And then I will narrate the unit symbol, right? Okay, let me just separate this so that you don't confuse that I'm writing about derived quantities, right? So let's just break this down, and then I will be giving you supplementary units as well. Let's call this as uh, supplementary units, right? Other units that are also used around the world. So these I'm going to narrate. So number one is length. The symbol is L or D. There are so many symbols in physics. You can use any symbol as long as you define what the symbol represents. So I'm going to represent length as L. We use D as well, right? So length is further named by many names like distance, displacement, height, width. So these are all different names of the base quantity, which is length, right? And its unit is actually meters. And when we talk about unit, I'm going to say that this is the SI unit, the System International. I'm going to get to what System International is in a while. Once I'm just going to define what these are, right? The symbol is M, right? And the supplementary units could be centimeter or kilometer or millimeters, and for some we have feet as well, right? So feet is also a unit. It's an American system, right, in which we have feet and miles, right? So these are all supplementary units which are also used, but the base unit or the the SI unit is meters, which is represented by this letter small m, right? On number two we have mass, right? Very common. It is represented by small m. Now understand that these are symbols, right? Quantity, I'm just going to put a Q over here so that you understand that I'm writing the symbols for quantity. Do not confuse this with M. That is why I'm putting these apostrophes over here so that you don't confuse these. Let me just change the color as well so that you understand that these are different. So I'm just going to use red. So L is this, then we have M, then next I will be using others as well in a moment. So for mass we have kilograms, so I'm just going to write kilograms, right? And it is represented by small k and a G. Do not write capital G, sorry, capital K. That represents kilo, right? That represents a quantity over here. So I'm just going to put a line over here so that that's the bit of a problem with the graphics tab, yeah, it's very hard to put straight lines over here. Okay, its kilogram. Supplementary units are grams, right? We have then milligrams, and then we have tons, right? So we've got so many units for this. Then next we actually have number three, which is the most, and these three are the most common, is time, right? It is represented by small t. I'm going to write the symbol in a moment, yeah, with the pink. Yeah, it's represented by t, small t, and it's measured in seconds, right? And then once we're its unit is actually seconds, which is small s. Supplementary units could be milliseconds or minutes or hours, HRS, right? These are the symbols that are used. Then we have days as well, days and years, days, months, and years, right? These are all supplementary units of time, right? So wherever any of these quantities are given to you in terms of these supplementary units, understand that we're talking about time, right? The next we're going to discuss is most common in chemistry. We don't use much of this in physics. It's called moles. It is represented by the small letter n, and the unit for this is actually moles, right? Just like the name of the quantity, and it is written by MOL dot, right? You don't need to put this full stop over here, but you can just write this MOL. Let me just extend those lines because we will be needing more of these lines for next quantities. Uh, and there are no supplementary units for this actually, so I'm just going to keep the supplementary empty over here. We have these three are the most common globally used uh, you can say quantities. So we can say that these are the most important three quantities. As I said, moles is mostly used in chemistry, so we're not going to have much of these supplementary units. It's a very specific quantity, unlike length, mass, and time, which is measured by many different, industries and many different purposes. So these do have supplementary units, right? Number five, and what these quantities are, I will explain in a moment. I don't think I need to explain mass or time, but moles is the quantity of substance, right? How much a substance is there, and especially translates into either mass or the number of particles, right? So we do have this formula over here, which is n is equal to small m, which is the given mass, over capital M, which is the mr, right? Or AR. So I'm just giving you as a reference from chemistry that this is what we use for moles. What moles is a number of it's a quantity of a substance. Number five, we have current, which is a very important term in physics. It is represented by the letter capital letter I, and the units for this is actually amperes, right? And it is represented by this word amp, or also A, right? We write A or for it, or amp. Both are available. The symbol is actually A as well. Amp is also a symbol. Both are used. Mostly A is used. Amp is very rarely used. So it could be milliamperes or mega amperes or kiloamperes, right? Or microamperes when we're talking about sensors. So these are the supplementary units for current. And moving on, then we have at number 6, right? And then the last one would be our number 7, which is the least used quantity or least heard quantity. Uh, uh, Over 6 we have temperature. Again, it is both used in chemistry and physics. It is represented by the symbol capital T, and sorry, let me just get the black one, right, so that you don't confuse that this is part of the symbol. These are just apostrophes. Okay, it is measured in Kelvin. Kelvin is the name of the scientist who developed the scale. It is represented by capital K, right? Understand that is why we don't use capital K for kilo or kilogram. Why? Because capital K represents temperature, and to not confuse the symbol of the quantity with the prefix, which I will discuss in a moment, that what are prefixes or suffixes. So this capital K is the unit, and we don't actually we actually have different kind of supplementary units, which is degree Celsius, right? Degree Fahrenheit, and we also have another absolute scale, which is Rankine, capital R. This is a very rare unit that is used. You're not going to know about this unit at least till you're into A levels, right? Or at least in engineering, this engineering unit which is used in some of the engineering applications. And number 7, the last quantity, is actually intensity of light, right? So that's the last base quantity that we measure. It is represented by this letter capital L, right? And that is why capital L is not used for length. We actually use D and stuff, D, S, and width, W for length. But for capital L will be used for intensity of light. The unit is candela. It is represented by this symbol CD. The supplementary units are lux, right? And we do know this soap brand by the name of Lux, which represents that your face is going to be shining like sun, right? So that's the supplementary unit for intensity of light, lux. So these are 7 base quantities upon which you are going to extract derived quantities, right? So now I'm going to get into derived quantities. Let me just switch the color. So what are now derived quantities, right? Now derived quantities are extracted uh, from base quantities, right? And similarly they will also have their own units. So I'm just going to again create a tabulator for this. I'm not going to explain many of these quantities because once I get into derived quantities, I know it's a very big chart that I will be making. So I'm just going to give you a few examples. I'm not going to write any supplementary units. Instead I'm going to donate some of the base units for it, right? So let's put the name of the quantity here. Let's put the quantity symbol. Then we have a unit for it, and then we have the unit symbol, and then we have uh, base units for that, right? And I'll tell you in a moment how you can find base units for a given quantity if you don't know the main unit, and then you can drive the unit for it. So number one is actually going to be area, right? And what is area? It is actually area is length into length, or length into width, right? Whatever you may call it. I'm just going to put length into length. Why? Because I just told you that length can be translated into length, width, height. So it can be, let me just say, it could be length, it could be width, right? It could be height, depth, whatever name you use it, those are all length. We also have then distance. Let me just write this over here on the site. Oh, there we go. Right, it could be distance, then we have displacement, then we have depth. So there's so many names for this. Thickness, so we can put any of this over here. All of these are lengths, right? So these are just different names for the simple base quantity which we call as length. So getting back to our derived quantities. Just get down. Yeah, there you go. Again, oh sorry, it's kind of hard to use the pen. That's why I prefer the mouse. Okay, now area is represented by a capital A. The units would be square meter, right? And it is represented as m power 2, and base units could be again, it is in meters, so it would be again meters square. Supplementary could be centimeter square or millimeter squares, but again, as I said, I won't be discussing supplementary units for this. That would be a very very big topic for us for the day. Okay, then next would be volume, right? So volume is actually represented by capital V. It is cubic cb meter, right? Represented by meter cube. Again, base units, in terms of base units, it would be meter cube. Moving on, we're going to have density, and we do know volume is length into length into length, right? And third, I'm going to discuss density. So density is going to be represented by this unique Greek symbol rho, right? And the units are actually not, you can say it is you know kilograms per cubic meter, right? And it would be kilogram per meter cube, and it is in -3, right? And there can be base units. Again, the base units are going to be the same, which is kilogram per meter cube. Furthermore, we can get into more of these base quantities, As I said, derived quantities are actually taken from base quantities, so I'm not going to represent much of these supplementary units. Next we have speed or velocity, right? Speed or velocity both actually have in terms of units, they are represented same. It is represented by small v. Its units are meter per second, right? So again, it is meter per second, and this is going to be in base units again, meter per second, right? So continuing on, now why I'm extending this table a little bit, because I want you to have a little idea of what base units of a derived quantity are and what are the SI units of the quantity are. And over here I just forgot that these are again SI units that I'm talking about. Base units could be also termed as SI units, but we also have non-SI units for some of the quantities. I'm just going to give you an example of it. For example, we have pressure, right? Number 5, let's talk about pressure. It is represented by capital P. The units are pascals, right? It is represented by PA. But for the base unit is going to be different from the the SI unit. We do know that pressure is force over area, and for velocity we have V is equal to D over T, which is length by time, right? Okay, and density is actually rho is equal to mass over volume, right? I'm just also writing formulas in case if you don't know the formulas. So when we talk about the base units, we understand that I will have to write the force over here as well, so that you understand what are the base units for force, because force also has a different SI unit and different base units. I'll get back to pressure in a moment, but first I'm going to write force as well, right? So force is represented by capital F. The units are newtons. Again, was discovered by Sir Isaac Newton. Sorry, that's Newton's gonna kill me for that. All right, Newton, right? And it is represented by capital N, and the base units for that are also calculated from its formula, which is force is mass into acceleration, right? So we do know that mass has certain unit. Now for that I again need to write another quantity, which is acceleration, and that's the last drive quantity I'm going to explain here, so that we just differentiate between base quantities and base units and SI units. So acceleration, and it is represented by small a. The units are meter per second squared, right? So that is going to be meter per second square. The base units are also per second square. Now for force, since it is mass into acceleration, so we're just going to sorry, I just raised my M. So we're going to write the base units for both of them as a product. So it is going to be kilogram for mass and multiplied by meter per second square for acceleration. Now since we have pressure over here, so we'll have to work a little bit on the base units for pressure. Again, it is going to be force, which is kilogram meter per second square, divided by area, which is meter squared. Now again, this m will be cancelled by this square, so we will get kilogram per meter. Since 1 meter is left, the square is cancelled by this m over here, and per second square. So you can always find the units for any given quantity from its formula using the base units. Just simply write the base units of each of the quantity. For example, for force, I also use these base units. If I don't know the base units for force, I can find that out using this formula over here, and then put it in this formula. and simply cut these things out which needs to be divided, and then I can get to the base unit. So this is the base unit for force and pressure, right? I hope some of these things are now clarified. What are these quantities and what we can do with these quantities? And now I will be looking into another unique topic, which is prefixes. So just let me get and start a new page over here. So let's call this as prefixes, and it's a very important topic for physics. I'm just going to move it after physical quantities. Let's talk about prefixes and what are prefixes, right? So let me just get a bigger one. Okay, so what's a prefix, right? Also let's scribble. So prefix, so as the name suggests, oh sorry, I think that's a little too much. Okay, what are prefixes? So as the name suggests, pre and we have fix. So now I'm just going to reduce the size. Yeah, there we go. So pre means something that comes okay, that looks more like games than comes. As at my joining writing, it's not very fruitful over here. Comes before, yeah, and fix, that is fixed with a unit, and we're talking about units of a quantity, unit of a quantity. So these are prefixes. So what are prefixes? What prefixes we already have, and what are the multiples? I'll tell you how to convert one into another. So first I'm just going to chart them out, starting from let's say unit, right? So unit is in numerals, we write it as 1, and then we have kilo, which is 10 to the power 3, right? Then we have mega, which is 10 to the power 6. I will write the symbols for them as well, right? The symbol is small k. For mega we have small capital M. For unit we don't have any specific symbol for it, and in negative we also have milli, which is 10 to the power minus 3, or 1 divided by 1000, and it is represented by small m. Then we have micro, 10 to the power minus 6. It is represented by a Greek symbol mu, right? And furthermore, we have nano, which is 10 to the power minus 9, represented by a small letter n with a little dash at the end. It's again a Greek symbol for n. And then we have pico, right? Which is 10 to the power minus 12, and it is represented by small p. And on top we have giga, which is 10 to the power 9, represented by capital G. And then we have tera, which is 10 to the power 12, represented by capital T, right? And these tera, giga, and mega you would know from computing devices. Terabytes, gigabytes, megabytes for the space allocation that you have on your devices for storage or RAM or whatsoever. So these are prefixes, and these prefixes are used in front of a quantity to be represented as a simple or base number. For example, let's say as an example, we have, for example, I give you a number. We have 20,000. You can say amperes, 20,000 amps, right, of current going through a power cable, right? From a powerhouse. So 20,000 is a big number. So I'm just going to cut these 3 zeros and just write 20 kiloamperes, right? Similarly, if we have, let's say, 44,000 volts coming in a power line, so I can rewrite this, right, as 44 uh, kilovolts, right? So this is how you use these quantities. Let's say we're talking about a lightning strike that is about that's very big number. So 1, 2, 3, 4, 5, 6, 7, and 8. So let's say these are 8 zeros. So let's see, 3 zeros here, 3 here, and then 3 of these digits over here. So now I'm going to incorporate the idea of scientific notation that we have discussed previously in one of the videos, what scientific notation is and how we need to write numbers, why we need to write these scientific numbers, why it's important, because it makes our data easier to read. So it is going to be 2 to the power 5, and this is now going to be 10 to the power. Well, let's move the decimal from here. So it is moving 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 places, so I will write 10 to the power 9. And this again further can be converted. I'm just going to write this is scientific notation as a reference so that you remember what scientific notation is, right? And then I'm going to convert this 10 to the power 9 into a prefix, right? The original unit is volts for lightning strike, so I'm just going to write it as 2.5 into 10 to the power, sorry, not 10 to the power, just a moment. Yeah, we were supposed to use the prefix, right? Okay, so it is going to be gigavolts, and that is the minimum amount of lightning strike potential that is there, right? So 10 to the power was giga, so we simply replaced it as is. So this is how you use prefixes. Now let's take another example of something of a smaller potential. Let's say we're talking about digital circuitry, so that's is like 0.00002 volts, very small little current coming from a sensor. So I can again first convert into scientific notation. So the decimal is going to move 1, 2, 3, 4, 5, and 6 places. So it is going to be 2.6 into 10 raised to the power minus 6 volts, right? And we do know that this 10 to the power minus 6 can further be converted into 2.6 microvolts, right? So that's correct, and this is also correct, but that's better. Why? Because this micro makes our job easier. If this 10 to the power 6 is not understood by some people, but micro would be understood. That's a small quantity of voltage. Now these were some simple examples of writing prefixes. At times we are given with numbers, let's say 0.00026 volts. So we can convert this into we can convert this into a scientific notation of 2.6 into 10 to the power minus 4 volts, and there's no conversion or prefix for 10 to the power minus 4. So I'm just going to break it down into multiple of 10 to the power 3. So it is going to 10 to the power minus 3 into 10 to the power minus 1, right? I simply separated this using the power rule from mathematics, and now I'm just going to convert it into 10 to the power 6. It is going to be into 10 to the power minus 1, and this I have converted into prefix millivolts, right? This is also correct, or I can simply write it as 0.26 millivolts, but this I'm not going to accept. Why I'm not going to accept this? Because this 0 is now the problem over here, right? Why? Because in scientific notation we discussed that the number should start from a non-zero number before the decimal, and since we put a 0 over here, so this is going to be incorrect. So I'm just simply going to remove this from the notebook so that no one else gets it wrong. So this is how you can convert these numbers, right? I hope I've clarified these two topics, which are very important: prefixes and physical quantities. If you have any questions left, please let me know in the comment section, or just send me a direct message. I'll try to respond as soon as possible, or send up a video response if your query is interesting enough to be discussed on a major platform. Thank you so much.